In Chapter 9, we will be looking at aromatic compounds, and what we have shown here is the structure of hemoglobin. Hemoglobin is used in our bodies to carry oxygen, and it contains a large aromatic cofactor called heme, and that is shown here. So those different rings here, and this whole thing makes up an aromatic compound, which is called heme. The term aromatic was used to describe some fragrant compounds, and they found this later to not be correct, and now it's used as a term to group together molecules that have similar chemical behaviors. We distinguish these from the alkane compounds or aliphatic compounds by their electron configurations. So benzene is our typical aromatic compound. We have that six-membered ring with the alternating double bonds. Benzaldehyde is another compound that's aromatic because it has the benzene ring plus this aldehyde group. We also have toluene, and this one here is the structure of Lipitor. And this is the structure of esterone, which is a weak estrogen steroid. So these aromatic compounds we can see all along here, and there's that one in the esterone. There's many common names for the different benzene derivatives. Toluene, which we saw on the last slide, and we see here also, can also be called methylbenzene, and aniline can be called aminobenzene. We see that one right here. Monosubstituted benzenes have systematic names as hydrocarbons with benzene. So benzene is kind of the parent name for these. So here we have bromobenzene, nitrobenzene, propylbenzene, because we have 3 carbons here. If you have a longer carbon chain than the 6 members in the benzene ring, we use benzene as a substituent, which is then called a phenyl group. So here we have 2-phenylheptane, and then if it's a benzene with the CH2 group, that's going to be a benzyl group. In the table here, we have some of the common aromatic names. There's toluene, phenol, aniline, acetophenone has this group here. Benzaldehyde we saw on the last slide. We have benzoic acid, xylene, and then the styrene here. The ones that you'll want to be familiar with include toluene, phenol, aniline, benzaldehyde, and benzoic acid. When we have 2 substituents on benzene, or they're also referred to as disubstituted benzenes, they can have different combinations of positions that are relative to each other. So if you have a compound that has a 1,2 substitution, that one is going to be considered ortho. So we have the chlorines here that are 1 and 2. So this one would be called ortho-dichlorobenzene. Or you could call it 1,2-dichlorobenzene. If it's 1,3 away from each other, this is a meta-dimethylbenzene. Or it's 1,3 disubstituted. And then if they're opposite each other, or 1,4, this is para. And in this case, our parent is not benzene, it's benzaldehyde. So this is para-chloro-benzaldehyde. Or it could be 4-chloro-benzaldehyde. When we go to name aromatic compounds, we want to choose the numbers to get lowest possible values. And this is especially important when you have more than 2 substituents. We're going to list the substituents alphabetically, and then we have the common names such as toluene, which we can consider. So in the structure of TNT, that's part of toluene. We'll see that in a second here. So in these examples, numbering the substituents this way is going to give us the lowest numbering versus if I had started 1 here. That would give us 1, 3, 4. This gives us 1, 2, 4. We're still going to list alphabetically. So this is 4-bromo, 1,2-dimethylbenzene. And then if I have an OH here, the parent is going to be phenol, and that's got to be 1. If your parent is one of the common ones, that's always going to be 1, and then we number around to give lowest numbering. So this will be 1,5-dimethylphenol. And then this is toluene is the parent because of that CH3. We have 3 nitro groups. This is 2,4,6 trinitrotoluene, or TNT. So to name these here, chlorine and bromine on a benzene do not have a special parent, so this will just be numbered to give us the lowest numbering. So this will be 1-bromo, 3-chlorobenzene. You can also call it metabromochlorobenzene. With 2 chlorines and a CH3, the CH3 is our parent, this toluene, that I'll number around to give the lowest numbering. So 2,5-dichlorotoluene. And then with an NH2, our parent is aniline. It's across from there, so I'm going to use parabromoaniline. Benzene is pretty stable because of resonance, and so when we do a reaction with benzene, it's going to react pretty slowly. If we want to do a bromine addition, we need to add a catalyst. And in this case, we're only going to add 1 bromine. So if we had an alkene, we added Br2. That's all we needed, because those are less stable. But because of resonance and an energy barrier, if we react Br2 with a catalyst present, we are still only going to add 1 bromine. The electron density in all 6 of these carbons is identical. Benzene is planar. The bond angles are 120. And each of the carbons has an sp2 and a p orbital that's perpendicular to the plane of the 6-membered rings. And what we can see here is a resonance structure where each of these pi bonds shifts over 1 carbon to give us that next one there. And oftentimes, benzene can also be represented with a circle because those electrons are always moving around. A heterocycle is a cyclic structure that has oxygen, nitrogen, or sulfur in the ring. There are many aromatic heterocycles, which we can see here. Pyridine and pyrimidine are present in our DNA, as are the ones along the bottom there, that cytosine, thymine, and uracil. We see histidine in amino acids, and pyrrole, imidazole, and thiophene are often used as organic bases in reactions. Polycyclic aromatic compounds are present in the environment. These have rings that are fused together, and there's multiple rings fused together. When they fuse together, they form these polycyclic aromatic hydrocarbons. These, a lot of times, are carcinogens. So naphthalene is in mothballs. We have anthracene, benzoate pyrene, and coronene. And we get exposure to these at different places. So these are these PAHs, or polycyclic aromatic hydrocarbons. So commonly, PAHs are released from burning coal. In oil, gas, tobacco especially, grilling will introduce PAHs into our biological systems. And a lot of these can get passed on to our waterways and then contaminate those by different emissions. Because they are carcinogens, they can lead to cancer. These can show up in soil, microorganisms, worms and insects, different vertebrates, and then they show up in our waterways. And here are some more of these PAHs. We have quinoline, isoquinoline. Indole is commonly in medications, actually, to combat these hydrocarbons. We have tryptophan, which is another amino acid. So these are all considered polycyclic aromatic hydrocarbons because they have multiple cyclic rings that are aromatic. So not all PAHs are carcinogenic. There are many reactions that we can do with benzene rings. We start with an aromatic ring. We can add carbon groups in terms of acylation, alkylation. We can add an OH, a sulfate, nitration, or different halogens. And all of these, when we do the reaction, keep the benzene core intact, so we're not losing bonds here. The first one that we saw a little bit of already is when we add bromine in the presence of an iron catalyst to give us 1Br. Our benzene stays intact. We add a Br here. And this goes through a lengthy mechanism that we're not going to get into this class, so you're not going to be responsible for this. But the bromine does do an electrophilic addition. And then it's going to be re-aromatized. So 1Br gets added. and benzene reforms. We can do this reaction with chlorine. Our benzene reforms, we add 1 chlorine. We can also do this reaction with iodine, but fluorine is too reactive, so we can't do a reaction where we add fluorine here. In either case, it's going to require this catalyst, and in the catalyst, halogen should match what you're trying to add. So if you wanted to do iodine, you'd want to add iron triiodide. We can add nitrate groups across the double onto a benzene ring, and what we do is we add nitric acid in the presence of sulfuric acid. When we mix those two things together, we form this nitronium ion. So that's the active species in the reaction when you add nitric acid with sulfuric acid. So that's why I have it shown here as the NO2 plus. And this is going to add an NO2 to the benzene ring. So that's one way to add a nitrate. If we add iron in the presence of acid followed by base, that will give us aniline. So we'll reduce that nitro group to the NH2 group. We can also add a sulfate group, and this reaction is often done with sulfur trioxide in the presence of sulfuric acid to give us this right here, and that goes into our reaction, which I've written as the SO3H plus to add SO3H. This reaction can be used in the process of making sulfanilamide, which is an antibiotic. Another reaction we can do is an alkylation, specifically a Friedel-Crafts reaction. These involve typically some carbon group with the aluminum trichloride catalyst. And here we have 2-chloropropane with the AlCl3 catalyst. And that will form this carbocation, which can then react with our benzene. We'll get an addition to that carbon right there. And then we're going to add that carbon there. These are one of the more useful reactions, and especially a different way of adding carbon-carbon bonds, which we haven't had too many of those reactions so far. But you do need to have that aluminum chloride catalyst in order to perform the reaction. So in these reactions, I might add this with AlCl3. And what I'll add is everything but the chlorine. And that's going to add right here. So here's my new bond. I have the methyl group that comes off and then 2 other carbons. There are limitations to the Friedel-Crafts reaction. This is only going to happen with the alkyl halides, but you can use fluorine, chlorine, iodine, bromine. So we can only use alkyl halides. Aryl halides will not work because they're too reactive, or halogens that are on a double bond. This also will not work with rings containing an amino group or a strongly electron withdrawing group. So if you try to do this reaction and Y equals any of these things, the reaction will not work. Okay, so if you had benzaldehyde and you wanted to do a Friedel-Crafts alkylation, that would not work. We can do reactions of acid chlorides as well, and this is an acylation because we're adding this here, this acyl group. So the R can be anything as long as we have that chlorine on the other side, and everything but the chlorine gets added. So we add this here similarly. So in this case, we're going to add everything but the chlorine group. to give us our R group that gets added via the Friedel-Crafts acylation. So if we look at a couple of practice problems here, we start with benzene. React benzene with chlorine. That's going to add 1 chlorine to the benzene ring and leave all of the double bonds alone. If I go down 1, this is a Friedel-Crafts alkylation. I'm going to add everything but the chlorine ring, but that's where it's going to attach to. And then again, I have a benzene with the halogen, so we're going to add 1 bromine, leaving the double bonds of benzene intact, and both of those involved catalysts. With this acyl group, we're going to add everything but that chlorine to do the Friedel-Crafts acylation. So I add the carbonyl and the R group that comes along with that. Having a substituent on benzene can change how quickly the reaction happens. We have some groups that are more reactive and some that are less reactive. And the substituents can also affect where the next group goes, so the positional relationship is controlled. Some groups on the ring can direct the next group that's being added to the ortho and or para position. So these are known as ortho-para directors. And we can also have meta-directors. So some groups can direct the next group to the meta position, and that's in relation to the group that's already on the ring. And how quickly the reaction occurs can also depend on what is on the ring. If I have a nitro group, that is going to slow the reaction down. So that would be 6 times 10 to the negative 8. Having a chloride on the ring is going to speed up the reaction a little bit. Benzene is just 1. And when I add an electron donating group, an OH here with the lone pairs on it, that's going to speed up the reaction 1,000 times. So we can see the reactivity trend here. The electron donating groups are stronger donators, and they speed up the reaction versus the electron withdrawing nitro groups, which slow down the reaction. So different substituents have different effects here. We can see that the reaction is fastest when we have electron donating groups. These electron lone pairs can donate into the ring from the NH2 or the OH, or the alkyl groups can donate through induction, and that's going to speed up the reaction. They have the lone pairs that can donate into the ring. The halogens also have lone pairs that can donate into the ring, but these are actually deactivators because they are electronegative and withdraw electron density. These are still ortho-para directors. They're kind of our oddball atoms here. Electron withdrawing groups are those groups that have an atom that is multiply bonded to another one. These pull electron density out of the ring and slow reactions down. They're deactivators and are also meta-directors. So this carbon has a double bond to oxygen. The sulfur, when you draw that out, has double bonds to 2 oxygens. And then we have the nitrile, which has 3 bonds to nitrogen. That's multiply bonded. So these are all electron withdrawing groups. They are deactivators that draw electron density out of the ring, and so are meta-directors. This shows a table of different activating groups and deactivating groups. We have the electron donating groups that are ortho-para directors, the deactivating halogens, and then our deactivating meta-directors. So what this tells us is where the next group on the ring is going to go. So if I have a CH3 group, that is an alkyl group that's activating, it's going to be an ortho-para director. So that means the next thing that gets added to the benzene ring, which is a chlorine, is going to go ortho and para. So in this first one I'm drawing here, our benzene ring stays the same. The CH3 stays put. We have an ortho-para director, so my first chlorine is going to go ortho. And we're going to get a mixture. We'll also get a para-chlorotoluene. This is the major product because of sterics. The chlorine has less obstacles in the para versus the ortho position. There's a methyl group there. In this next one, we have a C double bond O to a CH3. This is an electron withdrawing group. It's deactivating. It's a meta-director. When we add HNO3, this is going to add meta to that group that's already on the ring. And the meta group is 3 away. So the group that's on the ring is the bus driver. That determines where the next group goes. not the one that is getting added. So whatever is over the arrow is not the bus driver. So that Br2 is not going to tell us where the next group goes. The NH2 is the bus driver. It has lone pair electrons. It's electron donating. This is an ortho para director. So our Br is going to go ortho and para to the NH2. So here's our ortho bromine, and we're also going to get the para. In the next example, bromine is one of the deactivators that's an ortho para director. The ethyl group is going to get added. The CH2CH3 is not our direct, so we're going to get an ortho para here. And the R group that gets added is everything but the chlorine. So we're going to add 2 carbons. So that's the ortho, and then we'll get the para as well. Here we have lone pairs on that oxygen. This is not an electron withdrawing group. This is an electron donating group because the atom that's immediately bonded to the benzene has the lone pair, so that's electron donating. So we'll get ortho and para. Here is our para product. And lastly, we have a carbon double bonded to oxygen. This is an electron withdrawing group, so it's going to be a meta director. We have 1 product. A chlorine will be meta, which is 3 positions away from that carbonyl group.